Hi everybody, here we're going to discuss how to linearize graphs, and we're going to start with the simplest kind of graph first, which is going to be a linear graph. So here, let's just say you're given a table with a set of data points. So you have your x coordinates, and then you have your y coordinates, and what you want to do is to convert that into a graph. So you'll put your x's on the horizontal axis, and you'll plot your y's on the vertical axis. And when you do that, you should get data points that look like they're going along a line. And so here, the best fit for this is going to be a straight line, like this here, and it's going to have some slope m. So the equation that's going to describe this linear graph is going to be y equals the slope m times the x coordinate, or the let's just say x coordinate, plus the y-intercept b. That's going to be the first case, the simplest case. Now let's look at another case, another kind of graph that you can find when you're doing experiments. So this is going to be the case of a quadratic. So here, again, what you'll do is you'll do an experiment. You're going to measure some x, an x value and a y value, or an independent or a dependent variable. So you do your experiments, and you're going to get your independent variables to be a set of numbers here. And your measurements, you're going to plot, this is going to be your y coordinates here. And same thing, after you do your experiment, you want to convert that into a graph. And let's say here, let's do a graph. So x-axis, y-axis. Let's say here, though, you do your experiment and the data point, they're distributed like this. So here, clearly, this is not a linear graph. So the graph that looks like it's going to match more closely to this one is going to be some kind of a U-shaped graph. So there's different kinds of U-shaped graphs, but the simplest one is going to be this form: y equals some number c multiplied by x to the second power plus b. It's also possible that this is x to the fourth or x to the sixth, or some kind of even power. So just to make sure that the graph actually does depend on x to the second power, you'll do this. So what you'll do is you're going to create a new variable. You're going to call it t, and t is going to be equal to x to the second power. And you're going to create another new variable z, and z is going to be the same as y. And you're going to make a table using these two numbers. So this is going to be the t values, this is going to be the z values. So let's say, for example, that, let me just give some space here. So let's say that some of your numbers, so for example, for the original graph, you had 4 for the x and 8 for the y. So then here, what you're going to do is, the t is going to be then this column squared. So then a 4 is going to become, 4 squared is going to become a 16. And z is going to be the same as y. So z is going to stay 8. So you'll do that, do the calculations for all those numbers in the columns. And when you plot this one now, z versus t, so you're going to put t on this axis and z on this axis. And what you'll find is that you should get the numbers looking as if they're along a straight line again. And so here, the line that's going to best fit this one is going to be a straight line, and it's going to have a slope m. And the equation for the straight line is going to be z equals the slope m multiplied by the independent variable t, and multiplied by your new y-intercept, which is going to be a capital B. The next kind of graph that we're going to look at is going to be an exponential graph. So here, again, what's happening is that you're doing your experiment, and you're plotting your settings. That's going to be your x coordinates. So whatever you set your device to, that's going to be your x coordinates. And your measurements, the thing that you record after your experiment, those are going to be your y values. So you're just going to put your numbers here from when you do your experiment. So after you do your experiment, you're going to create a graph of those numbers. So you'll always put the x-axis, or the x values, on the horizontal and the y values on the vertical. And you're just going to transfer these data points onto this graph here. So let's say it looks something like this in this case. So again, you don't really know what the graph is going to look like. You're going to plot those data points, and that's going to tell you what the graph should look like. But let's say here, once you plot the data points, it looks something more like this. So here, this is not a linear graph. It's not a parabola either. The graph that looks like it's going to fit more closely to these points is going to be something like this here. So the graph that has this form is going to be an exponential. And so an exponential graph is going to have the general form y equals some number b multiplied by e raised to some number m times x. So that's going to be the form that's going to match this exponential growth here. But, you know, are we sure that it isn't? Is it e to the x or might be 2 to the x? We're not really sure. So you want to verify that the graph actually is e to the x. And so the way that you'll do that is you're going to now introduce a change of variables. You're going to set t equal to x, and you're going to set z equal to the natural log of y. And you're going to make another table. This time t is going to be on this side here, and then the dependent variable is going to be z. So let's say, again, let's just take your independent and dependent variables. Let's say that your independent variable is a 4, and your dependent variable is an 8. So t is going to be the same as x. So this is going to be the same as this one. So this is just going to be 4. Z, though, is going to be the natural log of y. So you'll take your y value, and you're going to take the natural log of that, and you'll put it here. So this should be the natural log of 8, or that should be about 2.08. And you'll do that for all of the rest of your numbers. And once you've created this new table, you're going to plot this now. So here, the independent variable is going to be t, and the dependent variable is going to be z. And so you're going to plot these numbers, these numbers versus these numbers here. And that should, again, give you a straight line. And so the line that's going to pass closest to all these numbers here is going to look more like a straight line with a slope m, and it's going to have a y-intercept, let's call it capital B. So here, the equation for this line is going to be z equals the slope m multiplied by the independent variable t and plus the y-intercept capital B. And the y-intercept capital B, that's actually going to be the natural log of the y-intercept from the original graph. The last one is going to be what's called a power graph. So again, the way that this works is that you do your experiments, you drop a ball and you measure the time for it. You have your stopwatch that measures time. So this is going to be what your instrument measures. And you can, from that, you can do some calculations. And so let's say that also you're going to do some measurement, another set of measurements, and you're going to plot those values here. So you do your experiment. This is just your measured values here. And let's say in this case here, again, you don't know what the graph is going to look like. You're going to plot it to see what the graph looks like. So then this is going to be x is going to be the horizontal, and y is going to be the vertical. And you're just going to transfer these data points onto this graph. And let's say here that it looks more like this. So let me actually try to redraw that. So let's say that here your data points look something like this. So here, this doesn't really look like an exponential, and it's definitely not a straight line or a parabola. So here, again, but you're not really sure what it is, so this looks like it's the best fit for this one is going to be not e to the x, but x raised to some number. So the general form for this one is going to be y equals some number b multiplied by x raised to some number m. But to be sure that this is the actual form of your data, so here what you're going to do is you're going to introduce another change of variables. You're going to set t equal to log base 10 of x, and you're going to set z equal to log base 10 of y. So what that means is that you're going to create another table. and you're going to put t on the independent side and z on the dependent side. But here what t is you have to go. So let's say again that let's pick our same numbers. Let's say that x is 4 and y is 8. So t is going to be log base 10 of 4, and that should give you about 0.6. And z, or y is 8, so z is going to be the natural log of 8, or excuse me, the log base 10 of 8, and that should give you about 0.9. And you're going to do that for all of the rest of the numbers here. And so now you're going to, the last kind of graph that we'll be looking at is you're going to do, again, the independent variable list here is t, and the dependent variable is z, and you're going to put these numbers onto this graph here. And when you do that, if your data point actually is a power relation, something like this, then you should get a straight line. And so the line that best fits these numbers is going to be a straight line. It's going to have a slope m, and it's going to have a y-intercept, let's call that capital B. And the equation for this one is going to, so this is a straight line again, so the equation is going to be z equals the slope m multiplied by the independent variable t and multiplied by the y-intercept capital B, where in this case here capital B is going to be log base 10 of b from the original graph. So these are the four main types of methods that you'll use to convert your measurements into a linearized graph.